Right, today we're going to look at some properties of matter, some changes it can go through, and just what those different properties represent, and also talk about chemical reactions a little bit. So starting here with the balloons, we might weigh an empty balloon and find that it weighs 2.8 or has a mass of 2.8 grams, and when I blow it up and fill it with air, perhaps its mass will go up to 3.2 grams. Obviously, the reason it does that is because there's something inside the balloon. In this case, it's the carbon dioxide I blew out. So the fact that there is a change in mass is evidence that there is some entity, some thing we call matter in that balloon after I've blown it up. So first of all, let's think about what mass is. Which of these seems to represent what mass is? So let's clarify that. Hopefully on the previous question, you chose the letter C, that mass is how much stuff something has, how much matter is in that object. Volume, on the other hand, is how much three-dimensional space an object takes up. So in the same way that I weighed a balloon, I could actually weigh a few paper clips, which take up much less space than a balloon, and I could find that they weigh about the same. So mass tells me how much stuff is actually there, whereas volume tells me how much room those objects are taking up. Now, just to make sure we have a definition of matter, matter is anything that has mass and takes up space. So if you have mass and you take up space, then you matter. Think about this before we get started. What's the fundamental building block of matter? See if you know that before we talk about it. If you said atom, you're correct. An atom is the smallest unit. The thing about an atom is it's going to have the same identity as the element itself. So if I look at copper, and I have a copper wire, and I break it down into the smallest, tiniest piece of copper wire I possibly can, even down to the point where I can't see it anymore, and I continue to break it down, the smallest part of copper that's still copper, we're going to call the atom. Now, I mentioned copper as an element. The periodic table of the elements holds all the elements. So if you're not sure whether or not something is an element, look to your periodic table. If it's on there directly, it's an element. If it's not, it's something we call a compound. So water would be an example of a compound. Water can be broken down into simpler substances, hydrogen and oxygen, because it's H2O. And then hydrogen and oxygen are the elements that make up the compound. So the key here is that an element is the simplest pure substance that can't be broken down into a simpler type of atom. A compound is made of two or more elements that are chemically bonded together. So we actually want to take a look at a sucrose molecule here. As you can see, we've got a few examples of molecules. We've got a water molecule, an oxygen molecule, and a sucrose molecule. Now, because the oxygen is only made up of one type of atom, it's two oxygen atoms formed together. This is actually an element because it's only containing oxygen. On the other hand, water and sucrose are both compounds because they contain more than one type of atom. Again, atoms are the basic form of an element, and any element can be found on the periodic table. So here we have the compound sugar, which is chemically known as sucrose, and we're holding it over a hot flame. We're going to allow it to heat up, and explore what happens to it. Kind of think, if you've seen sugar, notice it's starting to caramelize a little bit, and eventually you see something, you see some bubbles there. They're escaping, and you see the test tube kind of fogging up a little bit. That should be evidence of some new substances that are forming. And then notice the end of this burning, what we're going to be left with. So notice it becomes more solidified. There's less bubbles happening. And in the end, we have a final product that is much, much different than the original sucrose that we looked at. So what we actually did was we took this sucrose molecule and we broke it down into simpler parts. You notice the different atoms that make up the sucrose molecule include, we've got some carbon, some hydrogen, and some oxygen. So what we ended up doing was we got rid of some water vapor, so some H2Os. So the C12H22O11 was released, and we saw some water vapor escaping in the form of gas, and we also saw some carbon, the black stuff that was left over at the end. So we ended up with an element of carbon, and we ended up with a compound of water vapor. And we started with a compound of sucrose. So what's interesting, because water is a compound, we can actually break that down even further. And let me show you. This is actually something you can do at home, but we're going to use something called electrolysis to break that water compound down into its elements, which are H2 and O2. H2 is hydrogen gas. It's an element. And O2 is oxygen gas, which is also an element. Notice that they're both molecules. They both have more than one atom, but hydrogen and oxygen are two special types of atoms or elements called diatomic elements, meaning they will always form pairs with themselves. We'll talk about that later, but for now, just realize we're taking a compound that we already got from an earlier compound, and we're breaking it down into two separate elements. So you can see here we have just a simple cup with two thumbtacks inserted at the bottom, equally spaced, so that we can put a battery on there. And what the electricity is going to do is it's actually going to break up the water. We put a little baking soda into the water to make sure the electricity flows, but you can see the bubbles forming. You've got hydrogen and oxygen bubbles escaping from the liquid, going up into those test tubes and filling them up in the top there. And what's really cool is if you look closely, you see that the test tube on the right has about double the gas as the test tube on the left. Let me go back here. Notice how that right test tube has about twice as much gas as the one on the left. That's because hydrogen is on the right. We see that there's 2 volumes of hydrogen for every 1 volume of oxygen. And that's how scientists were early on able to determine that water has the formula H2O. So another example of a compound would be aspirin. And now aspirin obviously does not have the same properties as sugar. Sugar has a sweet taste to it. We don't eat aspirin, but I'm sure that it would have more of a bitter, unpleasant taste to it. And notice the structure is much different. With sucrose, notice how the different carbons, which are represented as green, are arranged, and the different oxygens, which are represented as red, and the hydrogens are blue. whereas here the structure is much different on the aspirin. You see there's like even a chain of carbon they're showing you there. Now, again, aspirin could be breaking down into carbon and hydrogen and oxygen just as the sugar could. Carbon is also used in graphite. It has that texture to it. If you've ever burned your toast, you see some carbon forming on the edge of your toast, indicating that it's burned. Now, I kind of just want to summarize what we were talking about in this diagram that I think is helpful to hopefully drive the point home. Again, elements, they can be found on the periodic table. The very basic building block of an element would be an atom. But elements can also come in molecules. There's 7 elements that are going to come as a diatomic molecule, such as oxygen and hydrogen, where we write O2 and H2. So elements can be made up of atoms or molecules. On the other hand, compounds cannot be made up of only one type of atom because they need to have multiple types of atoms. So the basic building block of a compound is a molecule, which is then built on atoms. So hopefully this helps you see the difference between elements and compounds. Elements are a pure substance that can't be broken into simpler substances. Compounds, on the other hand, can be broken down either into other compounds or atoms. So now I kind of want to switch gears here a little bit and talk about properties of matter. On these 2 slides, you notice we have 2 types. We've got what are called extensive properties, and then we're going to talk about intensive properties. So extensive properties depend on the amount of matter present. So we talked about the balloon earlier. The volume of that is going to change if I add more matter. If I add more air, the volume changes. The mass changes if I add more air because I have more stuff. There's more matter leading to a greater mass. Also, the amount of energy in a substance. If you're burning wood, there's some energy component to that, or gasoline in your car. If you have more of it, it's going to store more energy. So that depends on how much you have. It's very important that you have enough gas to get from point A to point B. So again, these are all extensive properties, meaning the amount is important. On the other hand, intensive properties, the amount is not as important. These are all properties that are inherent to the substance. So for instance, melting point, boiling point. If I have copper, it's going to melt at a certain point. It doesn't matter if I have a small piece of copper wire or if I have pennies. All those things, all those copper will melt at the same temperature. And water will always boil at the same temperature. It doesn't matter if I have a cup or a giant jug of water. I need to get that water to 100 degrees Celsius in order for it to boil. Again, these ideas of copper, water, or any other pure substance, sucrose, carbon dioxide, they're all going to have a specific density. I should be careful. Carbon dioxide is going to be dependent on temperature, but most solids, liquids, they're going to have a particular density that's associated with them. So copper will always have a particular density. Aluminum will always have a particular density. Again, unless the temperature changes, that density is something that we are sure of. It doesn't depend on how much I have. Same with conductivity. We're going to look at a list of intensive properties on this screen here. I'll zoom in so you can read some of these things. Conductivity just refers to the ability to carry either heat or electricity. Density is a volume or a mass to volume ratio. So how tightly packed is that material? Again, melting and boiling point is that temperature at which in terms of melting point, it's when the solid becomes a liquid. In terms of boiling point, it's when the liquid becomes a gas. We'll go into more detail with that in a second here. Index of refraction, if you've ever put a glass of water and put a pencil in there, you notice you can do what's called a broken pencil trick. in which the pencil appears to be two separate pencils because the water and the glass bend light so much that the pencil appears to be in a different place. That's why when you go diving, it's hard to if you're trying to retrieve something, it's hard to see exactly where it went. You have to kind of adjust, calibrate yourself to know where to jump in to get that item. Um, so index of refraction, more of a physics topic, but it's the bending, how much the material bends light. And then finally, malleability and ductility. Those are two possibly new ideas for you. If something's malleable, it's very easy to be manipulated or changed. So that's why silver makes good jewelry, because we can form that into different shapes. I think when I think of malleability, I think of aluminum sheets, because we can easily pound that aluminum down into very thin sheets. And what helps me remember it is that malleability, I think like mallet, because I can hammer it down into something else. Ductility is the ability to draw something into a thin wire. So again, I think of copper with this. We see copper is easily made into wires. Or in this example, they use a tantalum as a ductile metal used to make dental tools. That's just a summary of a lot of intensive properties. So I want to see if you were paying attention. Can you tell me which one of these four is the intensive property? So last year, we're going to look at physical properties and chemical properties. A physical property is something we can observe without changing the identity of the substance. So some examples of that, you might be surprised, but melting point and boiling point don't actually change the identity of the substance. If I have H2O, water, liquid form, and I freeze it, it becomes ice, which appears to be different, but it's still H2O. Same way if I go to boil it and I get that water vapor is still H2O. How do we know? If I were to hold a piece of glass above the water vapor, it would condense and turn back to liquid water. So melting and boiling are not chemical changes, they're actually physical changes. And a physical change, again, is a change where we don't change the identity. Anything like grinding, cutting, melting, boiling. If I had a piece of copper wire and I cut it in half, I still have copper. I didn't change the identity of the copper. If I were to cut paper, I might not be able to put it back together how it was, but it's only a physical change because I still have paper. Let's go a little bit deeper into that idea of change of state. A change of state is a physical change of one substance to another. So some examples would be the solid state, the liquid state, the gas state, and plasma. That's in order of how much energy it has. Solid state has the least energy, so its molecules or particles are packed tightly together. It has a definite volume and a definite shape. When we get a little more energy into it, it becomes a liquid. It's still going to have a volume we can measure, but the shape is going to take the shape of its container. Same with gas. Gas is going to take up the shape of its container, and it won't have a definite shape or a definite volume. And then we get even more energy. We get to the plasma state. That's at that point, the atoms are starting to break down a little bit and starting to become that plasma, sort of you think of if you've ever seen those plasma balls, the electricity that is happening there when the atoms are starting to break down. Just to give you a summary of the three, we're not going to talk about plasma a whole lot, but the solid state is when the atoms are tightly packed together. Again, definite shape, definite volume. Liquid, they start to flow past each other. no definite shape, but they do have a definite volume. We can measure how much space that liquid takes up. Gas, however, does not have a definite shape or a definite volume. It will fill its container. When we were burning that sugar, the fumes went all over the room. They filled up the room because the gas is able to spread apart and take the shape of its container. So tell me, which type of matter is it that has the definite shape and the definite volume? So last but not least, today we're going to talk about chemical properties and chemical changes. Chemical properties, in this case, we will transform it into a new substance. And in chemical reactions, we will see that change from one substance to another. So we're going to look at the reaction of aluminum and bromine. So here you see I have some aluminum foil in a form of liquid bromine, and we're going to place the bromine, which you can see some vapors on there. We're going to place the aluminum into the bromine. And kind of think of some of the observations you're making. What do you observe here when we put the aluminum into that bromine liquid? So it looks like a very violent reaction. Think, what kinds of things are you noticing? So hopefully you saw things like you noticed the light, the smoke that was coming, the vapors that were coming off of it. So hopefully you saw some of those different things and mentally noted them. You can probably assume there's some heat exchange there as well. But what that was an example of was a chemical reaction. We had two reactants. We had aluminum and bromine on one side, and then in the end it formed a new substance called aluminum bromide. So in a chemical reaction, to represent it, we always put the reactants on the left and the products on the right. So an example given here would be, sorry for the bell, but the carbon plus the oxygen is going to yield or form, that's what the arrow means. Arrow means yields or forms carbon dioxide. Remember, oxygen always comes in pairs, so I wrote O2. So carbon plus oxygen gives me carbon dioxide. These are my reactants. This is my product. So let's see if you can figure it out. If magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen, what are the reactants? So back to chemical changes. How do we know when a chemical change has occurred? How do we know we have a new substance? Go ahead and look at these four examples. We've got baking on the left. We've got baking soda and vinegar. You see bubbles. Bubbles are evidence that a gas has formed. The second picture, you actually started with two clear solutions, and when you mix them together, you ended up with a yellow salt. It was a solid that formed from the mixing of the two solutions. We call that a precipitate. kind of like precipitation is where the word comes from, precipitate. The third one is actually a thermite reaction. You see a lot of heat and light being formed there when aluminum reacts with iron 3 oxide. And finally, the last one, it might be a little hard to see, but that liquid actually turned slightly pink because when phenolphthalein is added to ammonia, we see it go from an odorless, colorless liquid to a pink solution. So these are all, so color change, heat and light, formation of a solid, formation of a gas and bubbles, those are all examples of chemical changes. We saw that with our electrolysis of water, right? We saw the bubbles form because we had two new substances. We started with water and we ended with hydrogen gas and oxygen gas. So just to summarize, we've got the burning of mercury oxide here. When we look at the mercury 2 oxide, some physical properties, we see that it's bright red, it's odorless, it doesn't dissolve in water well. On the other hand, chemical properties is what happens when it changes. So it decomposes, it turns into oxygen and mercury at a certain temperature. So on the other side, we have the products, oxygen and mercury, from when we burned the mercury 2 oxide. Physical properties of oxygen, it's colorless, it's odorless, it's soluble in water. That means it dissolves in water. It's how fish breathe. Some chemical properties, it combusts well. That's how the flame is happening. We've got methane combined with oxygen to form this flame. So oxygen combusts well. It reacts with a lot of metals. That's why you see oxidation. You see rust if you leave your bike out in the rain. A lot of things oxidize. Silver tarnishes because of oxygen. And then on the other hand, you see some physical properties of mercury. It's silver, like its color, what state it's in. It's ductile, it's malleable, you can cut it with a knife. But some of the chemical properties is that it forms alloys with most metals, it combines with sulfur, and it oxidizes with heating mercury 2 oxide. So just to sort of summarize some ideas for physical properties versus chemical properties. Here's another slide to do that as well. With the iron, physical property is that it's malleable and it's red. Chemical properties are, as you can see, it rusted. It reacted with oxygen. That's a chemical property. It also can react with bleach, and those are both chemical properties. So see if you can look at this list, pause the video if you need to, and think about whether each of these is a chemical property or a physical property.